Okay, so hello everyone. Welcome to the problem solving session for week 5 of the course Computational Commutative Algebra. So, so first I will list down the topics of this week 5. So let's start with the keywords. So in this week we started with by defining the prime irreducible ideals. Then we have defined associated primes of a module, and the set of all associated primes we have denoted it by as of M. Then we have seen a couple of properties of this set, like when it is non-empty and other things, that how this set behaves with short exact sequences and those things. Then from irreducible ideals, we have generalized this to irreducible submodules. So irreducible submodules. Then we have defined the notion of primary submodule of a module. So like if n is submodule of M, then n is primary, sorry, n is primary if and only if the associated primes of this quotient module is a singleton set. Uh, Likewise, and after defining primary submodule, we have defined primary decomposition of modules. So primary decomposition. Then we have proved a couple of properties or theorems, like when primary decomposition exists and some kind of uniqueness, and uniqueness of primary components related to the minimal primes or isolated primes, those things. Those are by just using localizations and all those things. After that, we have defined support of a module. Then minimal elements of this set is known as minimal primes of a module. We have seen these things coincide with the minimal elements of this set associated primes of M. So we have seen basically the properties of associated primes of a module and support of a module. So minimal primes of a module and properties of these things. And in the end, we have proved the so-called prime avoidance lemma. So the prime avoidance lemma. Then we have proved the existence of one kind of filtrations. So I will call that prime filtration. So using that, we have proved when the module is finitely generated over a Noetherian ring, then this set of associated primes is a finite set. So prime filtrations, and in the end, we have seen couple of examples. So how to dig out the associated primes or minimal primes, not in all cases, but some few cases we have seen. So we have seen using the concepts which we have learned in the earlier lectures. So these are the things which we have read in this week 5. So let's try to do some problems based on these concepts. Okay, so let me start with the first problem. So in this problem, we will try to see if we take the ring Z of integers, then how the irreducible ideals looks like. So our goal is to find the irreducible ideals in the ring Z of integers. So so we will eventually characterize all the irreducible ideals of Z. So now let P be a prime number and E be a positive integer. So this problem is from the practice problem set. So let E be a positive integer. Then prove that the ideal I generated by the element P power E in the ring Z is irreducible. So we have taken an ideal which is generated by a power of a prime number, and we need to prove that this ideal is an irreducible ideal in the ring of integers. So the question is very simple. So we need to prove that this ideal is irreducible. So how to prove that an ideal I is irreducible? So what is the definition? So definition is that I cannot be written as intersection of two ideals I1 and I2 where I is proper subset of I1 and I is proper subset of I2, and these are also proper ideals. So the ideal it cannot be written as intersection of two bigger proper ideals. Then we say that ideal is irreducible. So so let's solve this. So suppose uh, that I is not irreducible. So what this means? So then I can be written as intersection of two bigger proper ideals. So then I equals to I1 intersection I2, uh, where I is strictly subset of I1 and I2. These are strictly subset of Z. So I1 and I2 are two proper bigger ideals than I, and I is intersection of these two ideals. Now Z is a principal ideal domain. So every ideal in Z uh, is principal ideal. So let's use this fact. Okay, so I1 and I2 are principal ideals. So there exist A and B belongs to Z such that I1 is generated by A and I2 is generated by B. Now your the ideal P power E generated by P power E is basically equals to intersection of ideal generated by A and intersection with ideal generated by B. So what this means? So this means P power E belongs to ideal generated by A as well as P power E belongs to ideal generated by B. So this will imply A divides P power E and B also divides P power E. So A and B are integers which divides the power of prime. So that will imply A has to be some P power K1 and B has to be some P power K2. For some K1 and K2 greater equals to 1. So we can assume that one of K1 and K2, so without loss of generality, assume that this K1 is bigger equals to K2. And that will imply this ideal generated by A is subset of ideal generated by B. So this will imply ideal generated by A intersection ideal generated by B is basically equals to ideal generated by A. So this contradicts this irreducibility. So sorry, that I is not irreducible. So this is a contradiction. Hence, P power E is irreducible. So ideals of this form means ideals which are generated by some power of a prime number has to be irreducible in the ring of integers Z. Now let's do the next problem in which we will see uh, how to get the primary decomposition of an ideal in Z. So question number 2. So this is also from the practice problem sheet. So that if n equals to some p1 power e1 dot dot pr power er with pi's are, with pi's are prime numbers, with pi's are prime numbers and ei greater equals to 1 are positive integers, so this is for 1 less equals to y less equals to r, and pi's are actually distinct prime numbers with pi not equals to pj for I not equals to j, then so if you take the ideal generated by this number n, this is equals to ideal generated by p1 power e1 intersection ideal generated by pr power er. So this is actually is an irreducible primary decomposition or minimal primary decomposition. So basically, okay, we have to mention the ring. We should mention the ring. So irreducible primary decomposition of ideal generated by n in Z. So here in the ring Z, we know it is principal ideal domain. So we are taking an arbitrary ideal. So that is principal ideal. So it is generated by some integer. So let's take that integer n, and let's take its prime factorization as p1 power e1 dot dot pr power er. Now using this prime factorization, we will prove that if we take the ideal generated by n, then its minimal primary decomposition looks like this. So since p1 up to pr are already distinct primes, so these ideals p1 power e1 and up to pr power er all are distinct ideals. So what we have to prove in this case? So we need to prove it is irreducible primary decomposition. So we need to prove two things, that it is a primary decomposition and it is irreducible or minimal. So we have already proved that ideals of this form are already primary ideals in the previous exercise. So one part is already done. So first we will show uh, ideal generated by n is equal to the ideal generated by p1 power e1 intersection ideal generated by pr power er. So if we prove this equality, then we will prove that it is a primary decomposition. So let's prove this equality first. So one side is clear. So ideal generated by n is subset of this. So let's write down. So since n is p1 power e1 dot dot pr power er, clearly, okay, so it follows ideal generated by n is subset of ideal generated by p1 power e1 intersection ideal generated by pr power er. So this side is trivial. We need to prove the other side. So now let x is in the other side, means it is in the p1 power e1 intersection pr power er. So that will imply that p1 power e1, okay, let me write it clearly. So x belongs to ideal generated by p1 power, sorry, pi power ei for 1 less equals to I less equals to r, and this will imply pi power ei divides x for 1 less equals to I less equals to r. Now this will imply uh, LCM of p1 power e1 dot dot pr power er also divides x, but p1 pr p1 p2 up to pr all are distinct primes, so their LCM has to be their product. So p1 power e1 dot dot pr power er has to divide x. So n has to divide x. So that will imply x belongs to ideal generated by n. So we have proved the equality. So ideal generated by n equals to ideal generated by p1 power e1 intersection ideal generated by pr power er is a primary decomposition. Now we need to prove that it is irreducible or minimal primary decomposition. Now since P1 dot dot up to PR are distinct primes, so these are distinct primes, so we cannot remove any ideal in this intersection. This has to be minimal primary decomposition. So the above is a minimal primary decomposition. So this proves the complete. This proves completely the question. So now, if we take an arbitrary ideal in Z, we know its minimal primary decomposition. So from that, we can say about the associated primes. So let's put that as remark. So the first remark is if we take the ring Z and if we take the ideal NZ, then its associated primes. So we know NZ means basically ideal generated by N. Okay, so let's write in that form. So ideal generated by N, we know its primary decomposition looks like this. So these are the primary components, and radical of these primary components gives the associated primes, and radical of this is basically ideal generated by P1. So associated primes are basically ideal generated by P1 dot dot ideal generated by PR. So where N equals to P1 power E1 dot dot PR power ER is the prime factorization. So if we know the prime factorization of an integer, we can get the associated primes of the ideal generated by that integer. So this is one remark. The second remark is if we take a non-zero ideal, let's say I, which is generated by N, which is in Z. So this is so it is primary if and only if it is irreducible, if and only if I has the form P power E, where P is a prime number and E greater equals to 1 is an integer. So this gives the complete description of for non-zero primary or irreducible ideals. And the zero ideal is prime ideal because Z is an integral domain. So 0 is also primary as well as irreducible. And one more thing we can also conclude. So that I will not write, but I will tell. So if we take the polynomial ring in one variable, this is also a principal ideal domain. So if we take a non-zero ideal I, then it has to be generated by some single element, because it's principal ideal domain. Now if you take the element A and if you write its irreducible decomposition or irreducible factorization, it has the form some P1 power E1 up to PR power ER. Now using this irreducible factorization, one can get the minimal primary decomposition in the same way, and the conclusions will be same for polynomial ring in one variable. So that is just information for you. So for the ring of integers and for the polynomial ring in one variable over a field, we can give the description of primary decomposition of any ideal. So I hope it is clear. Mm. Okay, so let's move on. So let's see the next problem. Problem number 3. So recall that if we have a short exact sequence like 0 to m1 to m2 to m3 to 0, then we have a relation between the associated primes of these modules. So what is that relation? It is associated prime of the left one is subset of associated prime of the middle one, and the middle one, it is subset of associated primes of the extreme modules. Union of associated prime of the extreme modules. So now, so here we have subset equals to. So can we give an example where this is a proper subset? So let's write it down. So give an example of a short exact sequence of modules, let's say 0 to m1 to m2 to m3 to 0, such that the associated primes of the middle one is proper subset of associated prime of m1 union associated prime of m3. So we need to give an example where this is a proper subset. Okay, so let's see some example. So consider the short exact sequence of Z modules. So Z module means an abelian group. So this is 0 to 2Z to Z to Z mod 2Z to 0. So this is a short exact sequence. This is one standard short exact sequence. Now what about the associated primes of these three modules? Now as an so let's start with the middle one, associated prime of Z. So associated prime of Z over Z, what can we say? So I'm claiming this is only the ideal 0. So one reason is how the associated primes looks like. So these are all prime ideals which looks like annihilator of some element x, where x is a non-zero element of Z, right? Now if you take a non-zero element of Z, so if you take 0 not equals to n belongs to Z, then annihilator of the element n is basically 0. So whatever non-zero element you take, its annihilator has to be the zero ideal. So 0 is the only associated prime of Z. So that is one easy explanation, but there are other arguments also. Now, what about the associated primes of the lepton? Now, associated prime of 2Z over Z. So this is also 0. What is the reason? Because 2Z is isomorphic to Z as abelian groups. So these are isomorphic as Z module also. So they should have the same set of associated primes. Now what about the right one? So associated prime of Z mod 2Z over Z. So this we have done in the previous exercise. So these are we need to see the primary decomposition of the ideal generated by 2Z. Ideal generated by 2. So then we will get it is only the ideal generated by 2. So in this case, so associated prime of the middle one is proper subset associated prime of the extreme modules. So these are over all Z. So yes. Okay. So this is about associated primes of short exact sequences and associated primes and short exact sequences. Now let's move on to another problem. Okay, now let's try to find associated prime of a simple module. So find the set of all associated primes of the Z module uh, Z mod let's say 6Z direct sum Z mod 10Z. So Z mod 6Z and Z mod 10Z are Z modules. So their direct sum is also a Z module. So what will be the set of all associated primes of this direct sum? So how to find this one? So recall that if we have a split exact sequence uh, like a short exact sequence which has the form 0 to m1 to m1 direct sum m2 to m2 to 0, where the first map is just a goes to a comma 0 and the second map is m comma m prime mapped to just m prime, the projection map. So a short exact sequence of this form is called split exact sequence. So if we have split exact sequence or if we have direct sum, then associated prime of the middle one or the direct sum is basically associated prime of the extreme module. So here we have the equality. So let's use this fact. So we need to use this equality. So thus associated prime of Z mod 6Z direct sum Z mod 10Z over Z is basically associated prime of Z mod 6Z over Z union associated prime of Z mod 10Z over Z. So this is by using the previous fact, this one. So we need to find associated prime of Z mod 6Z and associated prime of Z mod 10Z. Now this thing we have already done. So this thing by using the primary decomposition of the ideal 6Z and primary decomposition of 10Z. So 6Z is basically, we need to look at the prime factorization of 6. So it is basically 2Z intersection 3Z. So these are prime ideals. And 10Z is basically 2Z intersection 5Z. Because 10 is 2 into 5 and 6 is 2 into 3. So these are primary decompositions. So this is basically 2Z, 3Z. These are the associated primes of the first module, Z mod 6Z, and union 2Z mod 3Z. So ultimately we are getting 2Z, 3Z and 5Z. So this module Z mod 6Z direct sum Z mod 10Z, this has three associated primes 2Z, 3Z and 5Z. So if we try to see it by the definition, means by using by finding the annihilator of elements like this, then it will be little bit difficult, but we can get the answer. But this is one convenient way of doing this, and by using the properties. So now here, if we take direct sum, then we have equality of associated primes of the individuals. Now instead of direct sum, if we take just usual sum, then what happens? Then can we get equality in that case? So this is question number 5. So let M be an R module where R is any ring, and M1, M2 be two submodules of M such that M is equals to M1 plus M2. Okay, so not direct sum, just usual sum. So then can we say that associated primes of M over the ring R equals to associated primes of M1 over R union associated primes of M2 over R? So instead of direct sum, if we take the usual sum, then can we have equality here? So let's try to see an example. So consider the Z module M, which is just Z direct sum Z mod 2Z, and M1 as the sum module M comma M bar. So this is collection of all the tuple M comma M bar such that M belongs to Z, and M2 as the sum module M comma 0 such that M belongs to Z. Then what are the okay, now if we take these two sum modules M1 and M2, then one can easily check that. Then one may check that M can be written as M1 plus M2. So this thing is easy to see. You just need to check that M is subset of M1 plus M2. So you just check by elements. That is not a difficult part. Now let's try to find the associated primes of these three modules. Now let's start with the easier one. What are the associated primes of M over Z? So this is basically associated prime of Z direct sum Z mod 3Z over Z. Since it is direct sum, so we can again use the same trick. So this is equals to associated prime of Z over Z union associated prime of Z mod 3Z over Z. So this is by again the previous trick. Now what about the associated primes of Z over Z and associated primes of Z mod 3Z over Z? So this one we have already seen. So this is just the zero ideal. And for Z mod 3Z, we again need to see the primary decomposition of the ideal 3Z. But 3Z is itself a prime ideal. So its associated prime is 3Z itself. So this is 3Z. So this is basically 0 and 3Z. So we have found the associated primes of the module M. Now we need to see associated primes of M1 and M2. So how to find the associated prime of M1 and associated primes of M2? So one thing you can observe that this M2 is actually isomorphic to Z because we only have the first coordinate non-zero. So observe that M2 is isomorphic to Z. So associated primes of M2 over Z is basically the 0. So that part, one part is easy, but what about associated primes of M1? So we will find it by definition. So we need to check any letter of non-zero elements of M1. Now let 0 not equals to M comma M bar belongs to M1. Then what can we say? Any letter of M comma M bar of this element over Z. So which elements of Z will annihilate this element? So if R belongs to Z such that R times M comma M bar equals to 0 comma 0 bar, So that will imply Rm comma Rm bar has to be 0 comma 0 bar, but that will imply Rm equals to 0. But M is non-zero and Z is a domain. So that will imply R has to be 0. So this annihilator has to be 0 ideal. So that means these associated primes of M1 over Z again has to be only 0 ideal. So both M1 and M2 has associated primes only 0, but M has 2 associated primes. So we are not getting equality here. So associated primes of M properly contains associated primes of M1 union associated primes of M2. So the answer is no. So we may not get equality in every case. So this equality may not happen. Okay, so let's try to see some other problems. So this is problem number 6. This is from the practice problem sheet again. So let R comma M be a Noetherian local ring and I be an ideal of R such that radical of I is M. So radical of I is M, that will imply that I is M primary. Now show the following things. So the first one is, so if we take the colon ideal I colon M, and if we take the quotient it by I, then this quotient is a non-zero R mod M module. Okay, R mod M vector space, because R mod M is a field. So a module over R mod M is basically a vector space over R mod M. So this is the first thing, that this quotient has to be a non-zero vector space over the field R mod M. Now part B. So this is a vector space. So it has some dimension. So if dimension of this vector space I colon M modulo I, so vector space over R mod M, so if this dimension is greater equals to 2, then I is not an irreducible ideal. Okay, so we are in a Noetherian local ring R comma M. I is an arbitrary ideal which is M primary, or its radical is M. Then we have to prove two things. The first one is this colon is a non-zero R-mod M vector space, and if the dimension of this quotient is a non-zero R-mod M vector space, and if the vector space dimension of this quotient is at least 2, then the ideal I cannot be irreducible. So let's prove these things one by one. So we have to prove that this thing is a R mod M vector space. So basically we need to prove it is a R mod M module. So to prove I colon M modulo I is a R mod M module, it is enough to prove that M is subset of annihilator of this module over R. That if this ideal annihilates this module, then this module has to be a module over the quotient. So for M belongs, for R belongs to the maximal ideal and A bar belongs to I colon M modulo I, then what happens this product? So what happens to this product R mod A bar? So this is basically RA plus I. But here this A belongs to I colon M. So that means if we multiply this element with an element of M, that has to be land in A. So this RA is an element of I. So this is basically same as 0 plus I or equals to 0 bar. So this implies M subset of annihilator of I colon M over I modulo I over R. So this proves that this quotient is a R mod M module. Now we need to prove that this is non-zero. So this quotient must have some non-zero element. So how to prove that one? So we need to prove that this colon is non-zero. So we will separate it in two cases. So if I is M primary, that is given. I is M primary. So if I is equals to M, then what about this colon? Sorry, this quotient. So this is basically R mod M, and this is a field. Then this has to be non-zero. So let I is a proper I sub. Okay, I is a proper ideal. So okay, I is a ideal which is properly contained in M. So then there exists X which is in M but not in I. But radical of I is M, so that will imply there exists N greater equals to 1 such that m power n is contained in I. So that will imply x power n is in I. But we can take, so here this n has to be 2 because x does not belongs to I. So n cannot be 1. So assume n greater equals to 1 such that x power n is in I, but x power n minus 1 is not in I. So we are taking n with this smallest possible n such that x power n is in I. So then consider the element x power n minus 1 plus I. So this is a non-zero element we need to prove. So this is not equals to 0 plus I because this is not in I. And if we take m and multiply it with x power n minus 1, then this is subset of m power n, that is subset of I. So that will imply x power n minus 1 belongs to I colon m. So that means x power n minus 1 plus I is a non-zero element in this quotient I colon m modulo I. So this quotient has to be non-zero. So this proves the first part of this problem, that this quotient is a non-zero R mod m vector space. Now let's move on to the second part. So the second part says that if the vector space dimension is at least 2, then I cannot be irreducible. So part B. Yes. So let the vector space dimension of this quotient I colon m modulo I over R mod m is at least 2. So we want to show I is not irreducible. That means I cannot be written as intersection of two proper bigger ideals than I. So this vector space dimension is 2. So it has two elements which are linearly independent. So let's take two elements. So let x bar comma y bar be a linearly independent set in this vector space. So these two vectors are linearly independent. So then if we take the subspace generated by x bar and take its intersection with the other subspace, then that has to be zero subspace, 0 in the vector space I mod m comma I, because these two are linearly independent vectors. So these two subspaces has to be uh, disjoint, means their intersection has to be 0. So now, so their intersection is 0. That means, so if we take the ideal generated by x, so so basically what we are doing, so here we are in R, and here we are in R mod m, and here I colon m mod I, this is a subspace of R mod m. Sorry, not a subspace, a vector space over R mod m. So here we have R I colon m mod I. Here we have taken two elements, x bar comma y bar. Now let's take the inverse image of these things. So that will be just x, sorry, let's take R mod I. Then this is a submodule of R mod I. Then their inverse image is, okay, let me write it here. So let J1 equals to ideal generated by x plus I, J2 equals to ideal generated by y plus the ideal I. Then this, so then J1 is the inverse image of this subspace. J2 is the inverse image of y bar. And since intersection of the subspaces is 0 in this column, means intersection of the inverse image has to be I. So then J1 intersection J2 is basically equals to I. And clearly J1 and J2 are bigger ideals than I, because it contains I, and they are not the whole ring. That is also clear. Thus I is not irreducible, because we have written I as intersection of two proper ideals which are bigger than I. So this proves the second part. So just remember this fact, that if you have a m primary ideal I, then if you have this vector space, and if you get the dimension is bigger than 2, then that ideal cannot be irreducible. Okay, let's use this to prove another fact. Okay, so one thing I want to mention before moving on to that part. So this is also from this another, this is a part of this problem, but I will not be doing this. So what happens if the dimension is exactly equal to 1? So if dimension of this quotient over R mod m equals to 1, then I has to be irreducible. One may try to prove this, but it will be easier to prove when we will see the concept of Artinian rings or finite length modules, those things. So you may try to prove this those after reading those things, but just take it as a information. Okay, So the next problem. So problem number 7. So let R be the polynomial ring kxy. Okay, one thing. So here we don't need actually local. We can take any maximal ideal. So let me write that. So let R be a Noetherian ring and M belongs to max spec of R. Then also it is fine. So now we can use this. So let R be this ring and I be the ideal generated by xy, its square. Then show that I is primary but not irreducible. So Kxy is an Noetherian ring by Hilbert basis theorem. So every ideal is finitely generated. So it has primary decomposition, and we can talk about primary and irreducible ideals. In the lectures, we have seen that irreducible ideal that will imply primary ideal, right? So irreducible implies primary, but this problem will show that the converse need not be true. So let's prove this. So observe that if we take the radical of I, so then it is just x comma y, the maximal ideal. So this is a maximal ideal. So if the radical is maximal ideal, then it has to be a primary ideal that uh, we already know from the lectures. So I is x comma y primary ideal. So it is m primary ideal. So we are in the situation that we have an m primary ideal. So we can use the previous exercise to test that this ideal is irreducible or not. So let's use the previous exercise. So now, okay, so let's use the notations. So let M be the maximal ideal generated by x comma y. Now then, what about this colon? I colon M in R. So this is basically R belongs to R such that M R subset of I. So you can check that this is exactly equals to M. So that means if you take this quotient, this is basically M mod I. So this is basically x comma y modulo x comma y square. So it is generated by two elements, and it is easy to check that this dimension of I colon m quotient by I over R mod m is exactly equals to 2. So since this dimension is bigger than 1, so this ideal has to be, I cannot be reducible. So by the previous exercise, I is not an irreducible ideal. So we can also write it as we can also write it as intersection of two bigger ideals by using the inverse image of uh, two linearly independent elements. So here it is easy to see this x bar and y bar is linearly independent. So note that. So we need to take the inverse image. So I, which is basically x comma y square. So we can write this is as x square xy y square. So this is basically uh, x square comma y intersection x comma y square. So this thing is inverse image of y bar. This thing is inverse image of x bar. So this from this we can directly say that I is not irreducible, but I is imprimary. So okay, I have written something wrong, I think. Yeah, this dimension has to be bigger equals to 2. If it is 1, then it has to be irreducible. Okay, let's do one problem related to the support of a module. So it is problem number 8. So let R be a Noetherian ring. R be a Noetherian ring. M be a finitely generated R module. So M be a finitely generated R module. Then so that so one thing is so for every prime ideal, if we every prime ideal P in the support, if we take the quotient M by P mod M Pm, then this quotient has to be non-zero. And the second thing is the converse is not true, and give an example to show that the converse of A need not be true. So we are in a Noetherian ring R and M be a finally generated module in that ring. Then we need to prove two things. Basically, we need to prove one thing, uh, and we need to give one counter example. So if P is a prime ideal in the support, then M mod Pm has to be non-zero. So this is from the practice problem sheet. So let's recall the support definition of support of M. So this is all those prime ideal in the spectrum such that localization of M at P is non-zero. So let's solve this. So let P belongs to support of M. So that means MP is a non-zero module. MP is a non-zero module, but using Nakayama's lemma, we can say that MP is not equals to PMP. So this is by the Nakayama's lemma, because RP mod PRP is a local ring and MP is finitely generated RP module. Why MP is finitely generated RP module? Because M is finitely generated RP. So we can take the same set of generators, image of the same set of generators. So then by using Nakayama's lemma, we can claim that this is not equal, because if equality holds, then MP has to be 0. So from this we can say MP mod PMP is non-zero. But what about this? So we know that localization commutes with short exact sequences. So this is basically M mod PM localized at P, and this is non-zero. But localization of a module is non-zero. That means the module itself has to be non-zero. And this proves the first part. So this is basically an application of the Nakayama's lemma. So Nakayama's lemma is a very powerful tool actually, but when we read for first time, we may not realize that how much powerful it is. So this is very easy actually. Now let's see the part B. So for part B, we need to give a counter example for the converse. So the converse is not true. So one example for this thing, one counter example. So basically let R equals to the polynomial ring in two variables over a field K. Let M be this module R quotient the ideal generated by X, and I be the ideal generated by Y. Then I is a prime ideal that we all know. Okay, not I. Let's take this as P, because it's a prime ideal. Now what about M quotient PM? So this is R quotient X modulo by ideal generated by Y times R quotient X. So this is same as R quotient X divided by ideal generated by Y plus ideal generated by X by ideal generated by X. So this is same as R going modulo ideal generated by X comma Y. But this is KXY modulo ideal generated by X comma Y. So this is isomorphic to K. So this is basically non-zero. So this quotient is non-zero. But if we take the support of M, so which is support of R quotient X. So this is support of KXY modulo X. So this is basically spectrum of kxy modulo x. So this is basically the prime ideals of kxy which contains x. So ideal generated by y does not contains x. So since ideal generated by y does not contains x, ideal generated by y does not belong to support of M. So this P does not belong to support of M, but still M mod PM is non-zero. So this proves that this converse is not true. So M mod PM is non-zero, that will not imply that P is in the support of M. But the converse is true in certain cases. So I will put that as a remark. So you may try to prove that. So if M is a maximal ideal such that M mod mm is non-zero, then M has to be in the support of M. So the converse is true in case of maximal ideals. So this you may try to prove this, but I will just put this as remark. Okay, so let's do one more problem. So problem number 9. So which of the following ideals ideals of the ring kx comma y, the polynomial ring kx comma y, is primary? So the first one is ideal generated by x cube y power 4. Second one is, okay, let's take x y z. So the second one is xz comma y, and the third one is ideal generated by x minus 2 y minus 4 z plus 5 q. So we have three ideals. We need to check which among these three ideals which are primary ideal. So let's check one by one. So ideal I is primary if and only if the associated prime of this quotient is a singleton set, or prime divisors of I is singleton. So let's use that fact. So what about the first ideal? It is x cube y power 4. Now observe that this can be written as ideal generated by x cube intersection y power 4. In fact, this is a primary decomposition. So associated prime of r mod x cube y power 4 is radical of this one and radical of this one, which is basically ideal generated by x and ideal generated by y. So it is not singleton. So it is not primary. So this one is not primary. So what about the second one? So it is xz comma y. So note that this can be written as x comma y intersection z comma y. So this is also primary decomposition and these are prime ideals. So this is basically ideal generated by x comma y and y comma z. So this has also cardinality too. This is also not primary. Now let's check the third one. So this is generated by x minus 2, y minus 4, z plus 5 square, and these three polynomials. Now let's try to find the uh, okay, let P be a prime ideal of R such that P contains this ideal I. Okay, now okay, I will tell why I am doing this. P contains I, that will imply x minus 2, y minus 4, and z plus 5 whole square. All these three elements belongs to P. Now that will imply x minus 2, y minus 4, and z plus 5 is also in P, because z plus 5 is a prime element. So its square belongs to P and P is prime ideal. So that will imply x minus 2, y minus 4, z plus 5. This ideal is subset of P. But this ideal is maximal because it corresponds to a single point 2 comma 4 comma minus 5. So that will imply P has to be equals to x minus 2, y minus 4, z plus 5. So there exists only one prime ideal which contains I. So this implies spec of R mod I, which is same as variety of I, is P, which is the ideal generated by x minus 2, y minus 4, z plus 5. So spec of R mod I is same as support of R mod I. And this is a singleton set. So this will be same as associated primes of R mod I. So it is a singleton set, and so it has to be because associated primes is subset of support, and it has to be non-empty because the quotient ring, it is non-zero, so it has to be singleton set. So this is primary ideal. So basically what we are getting, because radical of I is P and this is a maximal ideal. So since radical is a maximal ideal, so ideal has to be primary. So this will imply I is primary. So this checks all these three ideals which are primary and which are not. So similar type of problems you will find in the assignment sheet also. So try to do those problems. So yeah, so I think we have covered almost all the things. So maybe prime filtration, okay, we have not used those things. but the examples given in the lectures are good, so one may try to do some more examples like those examples from books. So I think we can stop here. Okay, so thank you.